In this video, we're going to look at the next case of finding the volume of a solid of revolution using a method which is called washers. So let's just review very quickly what the simple case was. So the simple case was when we had a function y is equal to f of x that was bounding our region above. We had the region bounded below by the x-axis, so the line y equals 0. So that is the area under the graph of f of x, from some bounds x equals a to x equals b. And so that region was revolved around the x-axis to create a solid of revolution here. There's our solid of revolution. And we looked at taking a single rectangle, taking a single rectangle like this one here, spinning it around, creating a single disk. And we worked with the volume of a disk being the area of the base, right? The volume of a disk is the area of the base times the height. And we worked through a Riemann sum with this and took a limit and got this formula, right? We got this formula for this very, very simple case where this pi r squared, that's the area of the base, dx is what happens to the delta x when n goes to infinity, and that radius ended up by being the function value, and so pi f of x squared dx is the general method here. And that is called typically the method of disks because that thing here, this little cylindrical-like object, is called a disk. So in this video, we're going to go one step a little further and complicate matters. So our next case here, we're going to have a lower bound. So instead of just the area under f of x, we're going to have a region that's bounded above by a function f of x, but now also has a lower bound. So the region is bounded below by g of x, and we'll keep our x equals a and x equals b as the left and the right, and we're going to keep revolving this around the x-axis. So here is our region here, and that region is revolved around the x-axis. And if that happens, what is created is a solid of revolution, which is hollow, right? So there's space here, right? There is space between the lower bound, g of x, and the x-axis, which is called the axis, the axis of revolution. And if there is space between the axis of revolution and the lower bound, then you get a hollow solid. And so what we have here, if we're trying to find a volume of this, then we're talking about the volume that is sort of contained in the thick walls, right? If I call this part sort of a wall of the solid, I'm talking about the volume in the thick walls. Another way of imagining it here is like a child's kind of arm floaty, right? Like this. So the solid is hollow. You can stick your arm right through the center if you were able to stick your arm through the x-axis here. And the volume that we're looking for is like finding the volume of the air that's in the floaty device. So the thick walls, that's the volume that we're looking for. So let's go over quickly how we might approach doing this. We're not going to do a full Riemann sum kind of situation, but we'll outline what you would do for this. So if we were creating a Riemann sum for area, we would be looking at rectangles, and we'd be looking at a single rectangle here as drawn in our region. Right? So we would be looking for a single rectangle here. And then we would sum up all those rectangles and such, but we want to see what happens if we take that single rectangle like we did in the previous case and spin that around, right? If we spin that around, again, there's going to be hollowness there. And if we spin that around, that space in the middle is going to create what is over here, which is the analogous object to a disk, except it's got a hole in the middle. And when it's got a hole in the middle, that object is no longer called a disk, but it's called a washer. And for those of you who don't know what washers are, they are these kind of objects right here. So if you've ever done any hardware stuff, you might have put a washer over your nuts and bolts and screw things in with this to protect the surface. So a washer is that kind of object, usually in metal, but you can have a rubber washer, let's say in a faucet or that sort of thing. So it's an object, a circular object with a hole in the middle. A more practical example from sort of everyday life, if you've ever had a Lifesaver candy. A Lifesaver candy is also the same kind of shape. Another colleague of mine liked calling them pineapple rings. Pineapple, I think I'm spelling this wrong, but you get the idea. Pineapple rings. So whatever whatever object helps you imagine the shape best is just fine. But that is the shape of the object. So instead of a disk, we have a washer, and we're going to be adding up washers all the way through to find the volume of the solid. And so the same way that we did for finding the volume of a single disk, the method of washers is going to find the volume of a single washer. It's then going to add up all the washers so that you have n washers, and finally it will let n go to infinity to give us an exact area, so exact volume. So what we want to do first of all is just get a handle on the volume of a single washer, and this is still a straight-sided three-dimensional object, and so the volume of the single washer is now the area of the base times the height, just like for a disk. The only deal is the area of the base it's not just a circle anymore. It's a circle with a hole in the middle. So how do you find the area of the base? Well, if you look over on this side, it's actually quite easy to imagine. So here is our washer, right? This is our washer shape. And so what we can do is just take the area of the big circle and subtract from it the missing little circle, right? So if we take the area of the big circle minus the area of the little circle, then you're going to get the area of the washer, which is going to be the area of the base, right? The area of the base that I'm talking about for our washer is this area right there, right? So that area of the base is absolutely a washer type shape. So if we say that the big circle has radius r and the little circle has radius little r, then when we do this subtraction, we have pi r squared, pi big R squared minus pi little r squared. And so if we factor out the pi, we get pi big R squared minus little r squared, and that is the area of the base. The height of our disk of our washer is delta x. Delta x, where does that come from? It comes from the width of the rectangle was delta x. That width gets spun around, and so that washer has thickness delta x, and when I flip the washer on its side, the height of the washer becomes delta x. So there's our formula in terms of geometry. Now what we need to see is how do our functions how do our functions play into these two radii? So if we look up again on the graph here, we're looking for the big radius, which we called big R, which is in green, and we're looking for the little radius, which is little r, which I've written in purple. And from the graph, it's pretty easy to see that the big radius is, well, it's from the axis of revolution. Remember, the x-axis that we're spinning around is called the axis of revolution. So our radius goes from the axis of revolution, which is the center of the circle, the axis of revolution to the furthest most point, and the furthest most point is on the function f of x. And so our outermost circle, the radius here of our outermost circle, big R, is f of x. And the same deal for our little circle, right? The little circle, the radius goes from the axis of revolution, from the center of the circle to the lowermost bound. That lowermost bound is g of x, and so the axis, the radius of our small circle, little r, is g of x, right? And so when you look at these things on the axes on the washer, as it is lying flat, you can see the green and the purple are there, and so indeed the big radius r and the little radius r, small r, are f and g in order. So filling in big R squared with capital F, with f of xi, filling in little r with g of xi for a single washer, we end up with this formula, which is the formula for, or the volume of a single washer. And then obviously we take it back into the formula here as I was talking about earlier, which is summing up to get first the volume approximately using n washers, and then taking the limit as n goes to infinity of that same formula, right? That same formula is our formula here for a single washer. We recognize the limit of the sum like that as a definite integral. And so the definite integral formula in our case is the integral from a to b of pi times b of f squared minus g squared dx, which is the correct formula for this situation, but is not the way that I usually think about it, or that most people usually think about it. So we think about this in kind of a memory aid type formula, which is this, that the volume is given as the integral from a to b of pi times big R squared. Big R was our f of x because it was on top, minus our little r squared. Little r squared was g of x because it was the lower bound. So this formula is sort of the more useful formula, and when we go into more complicated cases, this sort of memory aid formula here will still help, whereas the details of what the radii are, what the two different radiuses are is going to be slightly different. I just want to point out one last little thing here as well. If g of x was 0, if g of x, the bottom curve was 0, then the bottom curve would be the x-axis. And what would happen if g of x was 0? Well, then you'd end up by getting f of x squared minus 0, and you'd have exactly the same formula as we did in the simpler case. So this is really just a more general version of the formula that we had before.